Hi, everyone. Welcome to this lecture about confidence intervals. At a very high and informal level, the central limit theorem tells us that if we take a large enough sample from a population, then the sample mean will be close to the population mean. In this lecture, we will talk about confidence intervals, which use this insight from the central limit theorem to estimate a range of plausible values for a population parameter using a sample. A confidence interval is made up of a point estimate and an interval around that point, which shows our uncertainty about the estimate, the interval shows. Both of them, both the point and the interval, are calculated from a sample. Visually, we start with a number of points that make up our sample. That's what each blue dot represents in this visualization. We then come up with a point estimate, which is the mean of the sample. This is the red dot in the visualization. Finally, at both sides of the estimate, we have a confidence interval. The interval is symmetric around the point estimate and shows the range of plausible values for the population parameter. The margin of error is the distance from the point estimate to the endpoints of the interval. In other words, the confidence interval is the point estimate plus or minus the margin of error. The margin of error is half the width of the interval. So, how do we go about calculating the confidence interval? Well, let's remember the central limit theorem. What does the central limit theorem tell us? It says that if we take many large samples from a population, the distribution of the sample means will be approximately normally distributed. In this visual, you have a histogram of the sample means, which are normally distributed around the population mean. The red dashed line is the population mean, and the green dashed line is the sample mean, X bar. The X bar is just from one sample. If the sample means are normally distributed, and if we know the mean and standard deviation associated with that normal distribution, then we can talk about the probability of getting a sample mean within a certain range. For example, we can say that the probability of getting a sample mean within one standard deviation of the population mean is 68%, and we being within two standard deviations is approximately 95%. In other words, we can say that it is very unlikely to get a sample mean that is farther from the population mean given than a given number, and we can quantify that number if we know how much spread there is in the distribution of the sample means. So let's formalize this idea. We denoted the sample mean with X bar and sample size with N, population mean with mu, and population standard deviation with sigma. This means that the standard error, which is the standard deviation of the sampling distribution of sample means, is sigma divided by the square root of n. This was the central insight of the central limit theorem, that the standard error gets smaller as the sample size gets larger. So this is simply a restatement of the central limit theorem and of the plot that we just saw with mathematical notation. It says that the distribution of the sample means is approximately normally distributed with a mean of mu and standard deviation of sigma divided by square root of n. So now we ask the question, what is an interval around the population mean that contains 95% of the sample means, i.e. the X bar values? We can use R to find the quantiles of the normal distribution that contain 95% of the values. If we do the calculation, we would see that the quantiles are approximately minus 1.96 and plus 1.96, which means in a normal distribution, 95% of the values are within 1.96 standard deviations of the mean. Because the sample means are normally distributed around the population mean, we can say that 95% of the sample means are within 1.96 standard deviations of the population mean. We can write this as an inequality. In the middle, we have the sample mean, x bar, and it should be within 1.96 standard deviations of the population mean, mu. So we have the population mean mu here. We have 1.96 here. And because SEM, standard error of the mean, is the standard deviation of the sample means, we multiply that by 1.96 to get 1.96 standard deviations. And this is just the previous idea expressed as an inequality. And we can write this more explicitly by, instead of SEM, we can just write what the standard error of the mean is, which is, as we saw, sigma, the population standard deviation, divided by square root of the sample size. So we get this inequality. We can rearrange the terms of that inequality to get the population mean in the middle. So now we converted an interval around the population mean, where 95% of the sample means are expected to fall, into an interval around the sample mean, and the interval has the same width. This is a confidence interval for the population mean. It is a plausible range of values for the population mean at a given confidence level, in this case, 95%. Essentially, we are saying that if we can expect a large sample's mean to be close to the population mean, then the population's mean will also be close to the sample mean, and we are using the confidence interval to quantify how close it should be. The meaning of this inequality is that for 95% of all samples, the true population mean is within 1.96 standard deviations of the sample mean. Then the formula for 95% confidence interval becomes this formula, which is made more concise by the use of this plus minus notation. This part, where we multiply 1.96 with the standard error of the mean, is called the margin of error. So this is the margin of error. It is important to realize that 1.96 is not a magic number. We can construct a confidence interval at any level between 0 and 1 that we want. But 95% is the most common. For example, if we want a 99% confidence interval, we would use the quantiles of the normal distribution that contain 99% of the values, which are approximately minus 2.58 and plus 2.58. In this case, the margin of error is larger because we are looking at a wider range of values. We are seeking to be more confident in the plausibility of our interval, so we need to accommodate a larger range of values. But after all of this, here is one problem. We don't know this population standard deviation sigma. In practice, we only have a sample. So we use the sample standard deviation S as an estimate of the population standard deviation. The formula for the sample standard deviation is the square root of the sum of the square differences between each observation and the sample mean divided by n minus 1. The division by n minus 1 is called Bessel's correction, and it makes the sample standard deviation an almost unbiased estimator of the population standard deviation. And if you use the SD function in R, this is the calculation that it does. Now, as a result of not knowing the population standard deviation, we need to use the quantiles of the t distribution instead of the normal distribution. The t distribution accounts for the uncertainty of using the sample standard deviation, i.e., using sigma hat instead of sigma, the population standard deviation. The t distribution has heavier tails than the normal distribution, and how heavy the tails are depends on the sample size. Heavier tails will make the confidence interval wider, reflecting the uncertainty in the estimate of the population standard deviation. As the sample size increases, the t-distribution approaches the normal distribution. And this makes sense because the larger the sample size, the more confident we are about how the population really looks like. The increase in sample size is reflected in the degrees of freedom parameter of the t-distribution, which is the sample size minus 1. So the more correct formula is this formula, where we use the sample standard deviation, S, and the t quantile corresponding to the confidence level. The other parts are the same. Let's do a quick example in R to construct 95% confidence interval for the total family income variable in the census dataset. This dataset is from the open intro package, which contains and the dataset contains a random sample of 500 observations from the US Census in the year 2000. And I print only the first 3 rows of the dataset to give you an idea of what it looks like, and just to respect the space constraints that we have here. Okay, as a first step, we find the sample mean, x bar, of the total family income variable. We will ignore the missing values in this calculation. So we just take the mean, and the mean is 57,000 something. Next, we will calculate the margin of error, which has 3 components: the t quantile, the sample standard deviation, and the square root of the sample size. So we find the sample standard deviation S and the sample size N and exclude missing values here. We use the SD function to calculate the sample standard deviation and the length function to calculate the sample size. The sample standard deviation is around 70,000 and the sample size is 485 because we excluded missing values. Lastly, we need to find the t quantile corresponding to the confidence level. The degrees of freedom parameter of the t distribution is the sample size minus 1. In this case, the t quantile is about 1.96, which is very close to the normal quantile, and this is because the sample size is large. Generally, you would see 30 cited as the rule of thumb for when the t distribution is close enough to the normal distribution. In this case, it's much larger than that. Finally, we can bring it all together to calculate the confidence interval by plugging in the values we found into the formula. First, calculate the margin of error by multiplying the t quantile by the sample standard deviation and dividing the square root of the sample size. Then calculate the lower and upper bounds of the confidence interval by subtracting and adding the margin of error from the sample mean. And as a result, the 95% confidence interval is between approximately 51,000 and about 64,000. It is important to remember that there is always a confidence level associated with a confidence interval. In this case, it's 95%. If it were a 90% confidence interval, then the t quantile would be different and the interval would be narrower. If it were a 99% confidence interval, the t quantile would be different and the interval would be wider. The t.test function in R should give the same result as our manual calculation, and we can check that it really does. Okay, interpreting a confidence interval. Interpreting a confidence interval is the hardest part of the process. This is because we are tempted to say that there is a 95% probability that the true parameter is in this interval, but this is not true. Instead, we should say that 95% of confidence intervals calculated with this procedure would contain the true mean. The reason why this is so is because according to the frequentist interpretation of probability, the true parameter is fixed and the confidence interval is random. And confidence intervals are frequentist tools. So we cannot associate a probability with the true parameter being in the interval, since it's either in the interval or not. This is also at the heart of the difference between frequentist and Bayesian statistics. In Bayesian statistics, we can talk about the probability of the parameter being in an interval because we treat the parameter as a random variable. Our belief about where the parameter is can be quantified with a probability in the Bayesian framework, but that's not our topic for today. Okay, on a closing note, I would like to point you to a visual tool that can help you understand confidence intervals better. It is at rpsychologist.com/d3/CI. Please check it out. Thank you.